All right, so we're going to pick up here at 10.109 for part 2 of lesson 10.3.1, talking about the fundamental principle of counting. And really what we saw was there was a difference from the first problem to the second problem, because in the first problem you could repeat any number at each decision point for each digit. And on this one, really the difference was that after you made a choice, the number went down by 1 because now that number is taken out. So like I was explaining during the problem, in the first decision we have 7 choices, 1 through 7, but in the second choice we only have 6 choices because one of the numbers is now gone. And so when you're talking about explain the similarities and differences, well, the similarities are, we're still multiplying down, but the difference is we're dropping a number every time because a number is taken out every time we make a decision. All right, we'll see a kind of a mix of this on the next problem. So here's the introduction to this. The basis for a decision chart is the fundamental principle of counting. I will put up the math notes box at the end of this video, but make sure you go to the ebook at this point. I pause the video, go to the ebook, and look at that math notes box. They do a nice job explaining the fundamental principle of counting. You will have to go to the ebook to do that. But at the end of the lesson, we'll help you understand the fundamental principle of counting, but I'd like you to do it now. And then we're going to use decision charts here to answer each question. All right, and so the first one, a game contains 9 discs. Each one of the 9 has numbers 1, 2, 3, 4, 5, 6, 7, 8, or 9 on it. So each of the 9 discs has one number on it, 1 through 9. How many different 3-digit number combinations can be formed by choosing any 3 discs, and we can't replace the discs? All right, and so it's kind of like the last problem because we can't choose disc number 9 and then choose another disc number 9, and so we're going to have to go down down one choice each time. And then a good question to look at too is like how many different 3-digit number combinations can we form? That right there tells me that we're going to have 3 decisions to make. And so if I'm looking at A here, I have a first decision for the first one, a second, and a third decision, because I have a decision on the first digit, the second digit, and the third digit. On the first choice, or the first decision, I have 9 choices I could make. I could choose disc 1 through 9. All right. On the second decision, I only have 8 choices because I took one of the discs in the first decision, or the first choice. I took one of the discs, and it does say here I can't replace it. And so I have 9, and now I have 8 choices. And by the time I get to the third, I have 7 choices because I've taken something in the first and the second choice. All right. Now, like we did in problems 1 and problems 2, we multiply down our decision tree, and we'll have our answer for how many different combinations we can make, how many different 3-digit combinations we can make with discs numbered 1 through 9. And so we do 9 times 8 times 7, and I got to bring up my calculator quick. 9 times 8 times 7 gives me 504 different combinations that I can make in this circumstance. All right, excuse me. In part B, a new lotto game called Quick Spin has 3 wheels, each with the numbers 1 through 9 equally spaced around the rim. Each wheel is spun once, and the numbers the arrows point to are recorded in order. How many 3-digit numbers are possible this time? Well, here we have a little bit different than part A because each spin, so we have 3 decisions again because we get 3 spins. All right, in each spin you have a chance 1 through 9, and it doesn't say in here that numbers can't be repeated. So our assumption now is that numbers can be repeated. We could get a number 999, or we could get 888, or we could get 776. You could get that repetition of numbers, so it's going to change a little bit from what we saw in part A. So if we're looking at part B, we have 3 spins, right? It has 3 wheels, and so yeah, we're going to spin each one once. So there's going to be 3. There's going to be 3 decisions being made. You have a first spin, a second spin, and a third spin. Okay. In the first spin, you have 9 possible numbers it could land on, 1 through 9. Second spin, same thing. You have 9. Third spin, you have 9 because they're 3 separate wheels, numbers 1 through 9, and numbers can be repeated. All right. And then just like any decision that we've done so far, a decision chart we've done, multiply it on the decision chart, and you get 9 times 9 times 9, 9 to the third power, otherwise, if you like it that way. And that will give me 9 times 9 times 9 is 729 possible outcomes that we get in this quick spin game. Okay, part C, I'm just going to kind of, I don't want to write it out, I'll just talk about it. But for part C here, explain the similarities and the differences. Well, in part A and in part B, the similarities is that we have 3 decisions being made. All right, in this one, we are choosing 3 discs. And so you have one choice, 1 disc, 2 disc, 3 discs. And then in part B, we have 3 spins on 3 different wheels. So you have 1 spin, the 2nd spin, and the 3rd spin. But the difference is that one, it's not replacing the number. So you have 9, you had 9 discs, and then you take one out, so then you had 8 discs, then you take another one out, you have 7 discs. Whereas in B, you have 9 possible choices in spin 1, and then you're spinning another wheel that has 9 possible choices, and then you're spinning a third wheel that has 9 possible choices again. So we're not losing that, and we have that case kind of like we did in problem number 1, where we're just we're not losing a number every time. All right, and so we have that similarity, at least in the decisions, but the thing that's different is our choices for each decision. All right. This is the last one we're going to do here. But take a look. Maybe I'll talk about this one for a second if I have time, just because I want to get into this word factorial. But we will, let's take a look here first. So Marcos is selecting classes for next year. He plans to take English, physics, government, pre-calculus, Spanish, and journalism. His school has 6 periods, so he will have one of these classes for each period. All right. Now it's saying how many different schedules are possible. Okay? So if we're looking at A, we have 6 decisions to make, right? We have 6 classes, and each one of those classes is going to have, or we have 6 periods, and each one of those periods is going to have 6 choices for what class. And so the decisions we're making here, we have 1 decision, 1st, 2nd, 3rd, 4th, 5th, and 6th. Sorry for running out of room. Right? And then that's a decision, because there needs to be a decision made for each period of the day. All right? On the first one, for the first decision, for the first period of the day, there are 6 classes that are choices. Right? We have all 6 classes can be choices. You have English, physics, government, pre-calculus, Spanish, and journalism. Well, after that choice or after that decision is made, you only have 5 possible choices for second period because you already made a choice for first period. After second period, you have 4 choices. After third period, you have 3 choices, 2 choices, and 1 choice. Choices go down every time you make a decision because you can't repeat classes. Like you can't have first hour biology and second hour biology. It's just not going to happen. And so that's why we see this decrease in choices every time. Now it just becomes like what we saw with every kind of decision chart we've done. We're going to multiply down the decision chart down to here as well, which becomes a multiplication of 6 times 5 times 4 times 3 times 2 times 1. And just as like a little side bubble here, this is the idea of a factorial. And so what I just wrote out there is the same thing as if you ever saw 6 with this exclamation point. 6 factorial is the same thing as 6 times 5 times 4 times 3 times 2 times 1. That's a nice little actually segment into that. But we'll just focus on this right now. And I'm going to calculate this out. And so 6 times 5 times 4 times 3 times 2 times 1 gives me 720 possible choices or possible arrangements of this schedule. Okay, so 720 possible arrangements there. Now, we're going to take it a little bit further here. And it says how many schedules are possible if we have first period pre-calculus. All right, so first period pre-calculus means that we don't have 6 decisions anymore because one of those decisions was made. So we only have 5 decisions to make now. So we have first decision. We have first decision, second, third, fourth, and fifth. And I know I kind of did this because what happened was that we don't have a decision to make for first period. So really the first decision is for second period. Second decision is for third period. Third decision is for fourth, fifth, and so on. And what happens here is that when we're talking about that first decision, we only have 5 choices now for the first decision because we had 6 classes to choose from, but now pre-calculus is out of it, and so we only have 5 choices. After that first choice, we have 4. After the second choice, we have 3, 2, and then 1. And now we have our decision chart laid out. And like we've done before, we multiply through here. And so we get 5 times 4 times 3 times 2 times 1, which is another way of writing 5 factorial for fun. All right, and if I multiply this out, I have 5 times 4 times 3 times 2 times 1, and that is 120 possible choices if you know that you're taking pre-calculus first period of the day. Okay, so now it's saying what is the probability that you will get first period pre-calculus? Well, a nice way to do this is we can take all of our possible outcomes where we have pre-calculus first period and we can put them over our total sample space of 720. All right, and it's really the idea that we have it's kind of like we were doing with probability here. This is part C now, I believe. I haven't really been labeling these very well. That's A, this was B, now we're on C. But we have 720 total outcomes, 720 total outcomes, and 120 of those outcomes are pre-calculus first period, right? So 720 could be any class, any arrangement. 120 is the possible outcomes where you have pre-calculus first period. And so really what we have here is pre-calculus first period over the total number of outcomes, and that's going to give us our probability here. And so I could actually reduce this down here. I believe you can divide top and bottom by 120, which makes the numerator 1 and the denominator 6. And so you have a 1 in 6 chance that your schedule will give you pre-calculus first period. Now, I'm not for sure on this, but I think there might be some kind of correlation between their 6 classes. One of the classes is pre-calculus, and so there's a 1 in 6 chance that it ends up that way. I'm not 100% sure about that, but that's what I'm kind of going with here. I can think about that some more, but to keep going here. So now our next question is, what is the probability that Marcos will get first pre-calculus first period, pre-calculus first period and second period physics? Well, let's look at, if we look at D and we make a decision chart, we only now have 4 decisions being made, right? Because they're saying first period is pre-calculus, second period is physics. So now we only have 4 decisions being made. You have a decision for, your first decision would be for third period. Your second decision would be for fourth period. Your third decision would be for fifth period. And your fourth decision would be for sixth period, because the first 2 are already chosen for you. And so if you have 6 classes, 2 of them are taken because physics and pre-calc are taken. You now have 4 choices, 3 choices, 2 choices, and 1 choice. Multiplying down my decision tree, I see that I get 4 times 3 times 2 times 1. I don't even need my calculator here. 4 times 3 is 12. 12 times 2 is 24. 24 times 1 is 24. And so there's 24 possible outcomes that give you pre-calculus first and physics second. And so what we can do, similar to what we did last time, is 24 over 720, which reduces down to a 1 in 30 chance that you get pre-calculus first and physics second. Sorry, that was a little rushed there. Also, this is an example of 4 factorial. And I'm running out of time. Make sure you take a look at this math notes box. Either pause it here and look at it, or go to the ebook. And if you have any questions about the fundamental principle of counting or decision charts, please email me and let me know.